In this presentation, we will see all kinds of volumes that are part of the AP Calculus AB curriculum. We will go in clockwise order and see different examples of volumes in terms of X, volumes in terms of Y, and volumes by cross-sections, washers, disks, etc. And you can refer to these images later on if you want to see one of these specific examples again. Now, all of these examples are based on one important formula, and that formula is this one here. It's the overarching formula in the sense that you can always use them for any exercise that you try to solve. The volume is the integral from a to b of the area in terms of x dx. We will see that there are many variations on that formula depending on the situation. In particular, it might be an integral in terms of y, so it would be a of y dy. Now, I would recommend that when you try to solve a problem that is given, you go through a certain number of steps. You don't have to go through every single one of these steps, but it really helps to have a general idea of some of the setups and graphing that you may want to do in order to be successful. In terms of graphing, you surely want to draw the function that you are given, or maybe the functions if there are two of them. You want to then identify the region. This is going to be done with the functions and maybe the limits of the integral. Then you may want to sketch the volume to have an idea of what it looks like. And then you should probably also draw a disk or a washer if it's a washer, or a cross-section, just to have a visual that you can use later on for identifying the important dimensions. Among these dimensions, there might be the radius, but if it's a cross-section and the shape is a triangle, maybe you want to add where the base is and where the height is. We will see examples of that. After you've done all this graphing, the integral setup means you're going to have to figure out which variable we are going to use. Is it an integral in terms of x or y? You're going to want to figure out what the limits of integration are, and you will try to express the radius or the base and the height, etc. algebraically, and finally you can set up the integral. Once you're done with all that, the rest is just solving because you've managed to transfer from maybe a word problem to an equation, and you just have to solve the integral. We will not focus on solving the integral much in this presentation. It's really about the setup. So our first example is a volume in terms of x. We will use disks, and it's going to be probably the easiest of all the examples. Here's the question. Consider the region bounded by y equals x squared, the x-axis, and x equals 3. Here you can see that we have 3 elements that bound our region. There may be probably up to 4. If there's a left side, a right side, a top and a bottom, maybe, although it's not always like that. Here, apparently 3 is enough to bound a region. The question is, what is the volume of the solid generated when that region is rotated about the x-axis? Okay, so firstly we want to sketch the function y equals x squared, and then we will add the other boundaries. So the x-axis corresponds to y equals 0, and then we also have x equals 3. These 3 graphs clearly define a region that is represented here. It's not a triangle, so you should not use a formula for the area of a triangle, because the top left is slightly curved. After that, it's a good idea to sketch the volume as it is rotated about the x-axis. You can see that I also added an extra little disk here. So we have the very end of our volume here, a huge disk, but we have a small one there. And these disks are going to increase in size as x travels from 0 to 3. I also added where the radius is. So I did not show the disk that corresponds to this radius, but you could probably imagine that there's a disk here for this radius. Once you've done that, you've done plenty enough for sketching, and it will really help you, support you when you are trying to set up the integral. So the volume, as we saw, has this overarching formula, is the integral from a to b of x dx. We need to find first probably whether we're going to be integrating in terms of x or y. And the good thing is, the good way to think about it is to imagine several of these disks. There's infinitely many starting at x equals 0, and then there's this one, and then there's one where the r is represented, and so on, all the way to the last one at x equals 3. So you can see that in order to visit all these disks, we are going to have to vary the x from 0, and we will travel along the x-axis until we reach x equals 3. That tells you that we need to integrate in terms of x. With that, we can also automatically figure out that the first disk is at x equals 0, and the last one is at x equals 3. So we can set up the limits of integration. Because these are disks, the formula for the area is pi r squared. The issue is r is not x, so we need to express r in terms of x. That's where our sketch helps again. The radius, as you can see, is actually exactly x squared. If I chose an x here at, let's say, 1.4, then the radius would be 1.4 squared. So I substitute r equals x squared. Notice how r was squared as well, so we have x squared squared, and that becomes x power 4. You can typically take the pi out because it's a constant, and our volume is going to be the pi times the integral from 0 to 3 of x power 4 dx. From here on, we will see example after example that are variations on the same theme. For every example, I have added in green what has changed since the previous example. So this time we're looking at volumes in terms of x, disks again, but we will see that we are not rotating about the x-axis anymore. This time, consider the region bounded by y equals x squared, y equals -2, x equals 0, and x equals 3. This time there are 4 boundaries to define the region. What is the volume of the solid generated when that region is rotated about y equals -2? Another difference, we are not rotating about the x-axis, but about y equals -2. So, what does it look like? The region used to be the triangle here, but we have now changed that. We have changed it to adding x equals 0 as a boundary, and instead of the x-axis we have y equals -2 as a boundary. So our region is slightly greater. Also, we used to rotate about the x-axis on the left, but now we are rotating about y equals -2. So you can see how the disks are going to be significantly larger, all of them. The first one, it used to not even be a disk really, and then each one is bigger than it used to be. In fact, our radius will say a lot here. The radius is bigger, and it's quite easy to notice that it's 2 units bigger than it was in the previous example. Back to our overarching formula, v is the integral from a to b of a of x dx. It is the same limits. We are integrating from x equals 0 to x equals 3. We are confident that we have to integrate in terms of x, because to visit all these disks, we can see 3 on the image, the first blue one, then the pink one, and then the last one. It's x that needs to vary from 0 to 3. The difference is that the radius now is 2 bigger than it was before. So we have this part here, which is f of x. In our example, this is x squared, but we have plus 2 because each of these disks has an extra 2 units of radius. So it boils down to r being equal to x squared plus 2, and this is the integral. If you want to integrate that, you surely are going to distribute, and maybe you'll pull out the pi, and then you can solve the integral. The next example we are going to see is not with disks anymore, but with washers. It's still volumes in terms of x, but with washers. Consider the region bounded by y equals x squared, y equals x squared over 2, and x equals 3. What is the volume of the solid generated when that region is rotated about the x-axis. So what's changed here is that instead of having the x-axis as the bottom boundary, we have another function, y equals x squared over 2. By the way, these are washers which you use in Handicraft. So on the left you can see the region we used to have in the first exercise, and now on the right the region we're going to be working with in this example. In fact, the way to think about the region that we are going to work with in this example is to imagine we have the original region and then we're going to subtract this region. So earlier, with the first example, we had a volume that looked like this. Now our volume is different. It has a hole in it. All of this part here is actually hollow. We kind of dug into the volume we had earlier and removed that part of it. So that makes us realize that to find the volume in this example, what we're going to have to do is to calculate the volume that we found earlier and then subtract the volume of this little part here. This is why we call these washers. It's actually a disk minus a smaller disk. So this time we need to adapt our overarching formula a little bit. We actually have two of them. We will have the volume of the exercise we did very early on minus the volume of the whole. We typically don't write two integrals like that, even though you're welcome to, because we can simply put both of them into one. The limits of the integral are also x equals 0 and x equals 3, just like earlier. Now, the area of the larger disk, the one that goes all the way here and all the way down, is defined by the first radius, the radius that extends from the x-axis to y equals x squared. So it's a certain radius that I call R1. On the other hand, the volume of the whole is going to be defined with a second radius, R2. It is not the same. So area 1 is pi times R1 squared, and area 2 is pi times R2 squared. Our sketch helps us figure out what R1 and R2 are equal to. R1 is x squared, R2 is x squared over 2, and so we can substitute these values and then simplify a little bit. I could keep on simplifying from here, but we've now definitely set up our integral and the issue is different. It's just solving an integral. From here on, we're going to focus a little bit on integrating in terms of y. You can see again how the disks here were vertical, the disk is vertical, the washer is vertical, and in our new example, the washer is horizontal. Consider the region bounded by y equals x squared, the x-axis, and x equals 3. What is the region of the solid generated when that region is rotated about the y-axis? We have exactly the same region as before. The only difference in this question is that we are rotating that region about the y-axis. What happens when we rotate about the y-axis? The volume we obtain is significantly different from earlier. This looks maybe like a glass. It is hollow here, and it is full here and there. So how would we notice that this example requires us to integrate in terms of y? Well, you can imagine that all these disks or washers are piled up from the very bottom one all the way to the top one here, and if we want to visit all of them, we need to travel along the y-axis. We need to start at y equals 0, reach this one, which might be at y equals 2.5 or something, keep on going up. There's more here represented with these R1, R2, and the last one is going to be at y equals 9. One thing that we will want to notice right away is that R1 is actually constant. if you imagine going along the y-axis and starting at the bottom, R1 is always equal to 3. It's 3 here, it's 3 there, and it's 3 all the way up. Because what we're doing here is we are going to calculate the volume of the cylinder and then subtract the volume of this hollowness. So the volume of a cylinder, we actually don't need calculus. In this presentation, I will use calculus. I will just use the overarching formula because we want to practice that. But in reality, when you are solving exercises, you might as well use pi r squared times h to find the volume of the cylinder and then subtract the whole. For R2, it's a bit more difficult. How can we express R2? In particular, we need to express R2 in terms of y because we have an integral in terms of y. So to do that, we want to notice that for any point that I pick on the parabola, the point is always defined with the x-coordinate and the y-coordinate. And R2, the value of the radius for the inner disk, the disk that's going to define the hole, it's actually the value of x. But we can't use x because we are integrating in terms of y. R2 is the value of x, so R2 equals x, but we want it expressed in terms of y. So we need to solve y equals x squared and say x equals square root of y. So R2 is equal to the square root of y. Alright, so we are integrating a y dy. We need to figure out from where to where we are going. And notice that this time it's different. We are not integrating from 0 to 3 because it used to be we integrate from x equals 0 to x equals 3. But now that we integrate in terms of y, we are actually going from y equals 0 all the way to y equals 9. How do I find this 9? Well, remember that we are on the graph of y equals x squared. So if x equals 3, x squared equals 9. So y equals 9. And then we can just set up one integral a1 of y minus a2 of y, and we substitute r1, we substitute r2, and we get an integral that we can solve. In the beginning, when we were finding the area between two graphs, or when we were integrating in terms of x, we often said that we were integrating the top function minus the bottom function. It becomes increasingly difficult now, and it's not always top minus bottom. In this example right here, it's the right part minus the left part, because our volume is defined by these two rotation. When we rotate this vertical line to create the cylinder, and when we rotate this parabola to create the hole. So it's probably better to not think top minus bottom, not even to think right minus left, but to think further minus closer. What is the furthest part to the axis of rotation? Here the y-axis. And what is the closest part? The furthest part is x equals 3. And the closest part is the parabola. More examples, and somehow we get to an easier example now. I thought, how about having the same region, but instead of integrating about the y-axis, what if we decide to rotate about the line x equals 3? So the region is exactly the same. It's defined by y equals x squared, the x-axis, and x equals 3. The only difference is we are now rotating about x equals 3. See what happens? The axis of rotation is x equals 3, so this region that we're integrating turns this way. And we are kind of lucky. You may realize right now that we are not using washers here. There is no hole in the middle. There is only a volume, only a disk, not washer. It's really good to draw a disk in this example and to sketch the radius. This is going to be the hardest thing in this example, how to express the radius. Well, to do that, notice how from the y-axis all the way to the axis of rotation, there's a length of 3, and it's constant from top to bottom, or bottom to top. R is actually 3 minus the x value. we just talked about earlier how this is equal to x. So if we did 3 minus x, we would get the radius. Since we are integrating in terms of y, it's 3 minus the square root of y. Let's talk again about how we can be convinced we will need to integrate in terms of y. If I look at the bottom disk here, and I look at the pink one, and I would think about another disk up here, we notice how they are stacked. We need to travel along the y-axis to visit each of these disks. We're going to start at y equals 0, and it's going to give us a disk. We're going to reach y equals 1.9, and it'll give us the pink disk, and we will go all the way up to y equals 9. So we can set up the integral. The limits are 0 and 9. R is 3 minus the square root of y, and this is our setup. We would need to distribute and then solve. It's not very difficult from here. That was really convenient that we picked the axis of rotation to be x equals 3. What if we picked an axis of rotation that was even beyond 3? In this example, we're keeping the same region and we're rotating it about x equals 4. This is what it's going to look like. Now our region, which is here, is rotating all the way there, and it has created a hole in it. All of the cylinder here is hollow, so we are going to have to be careful and subtract that volume. Immediately we can see how, by maybe sketching a disc or two, we have a washer, not a disc anymore. It's 2 discs, in fact. I've added a 4 here. That's definitely going to help us with something when we identify how to express R1 and R2. Think about whether this is going to be an integral in terms of x or y. Well, it's definitely going to be in terms of y. The bottom washer can be seen here. There's another washer here in pink, and they keep on stacking vertically. So we are traveling along the y-axis, visiting each of our washers until we reach y equals 9. R1 is the one that is further from the axis of rotation. So it's going to be the one that we're going to use first, and then we will subtract the closer one. So R1 is 4 minus the value of x, just like before. Therefore, it's 4 minus the square root of y. R2, we are again in an easy situation here, because R2, no matter where you are from y equals 0 to y equals 9, R2 is constant. It's always equal to 1. Technically, it's 4 minus 3. X equals 4 is this line, and then x equals 3 is that line. Therefore, R2 is 4 minus 3 equals 1. Once again, in order to subtract the volume of this cylinder in the middle, you would not need calculus. You could just use pi r squared h, but I'm going to stick to the overarching formula. There is not much to say here. We have the overarching formula. We have washers, therefore we use A1 minus A2. A1 represents the furthest part, A2 represents the closest part to the axis of rotation, and we get this in the end, which you would have to work a little to solve. That is all that we're going to see about volumes of revolution. We've seen 6 examples, and they all have varieties, but I think they cover pretty much every case you could ever encounter. Now we're going to look at 2 volumes by cross-sections. The first one is a volume in terms of x. The region bounded by y equals x squared, the x-axis, and x equals 3 is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a right triangle whose height is 1/2 of its base, which lies in the region. There's a lot of differences here because we are not rotating the region. We are expressing it with saying that it is the base of a solid and then describing what the solid looks like. So the region is the same. We've seen that it is the base of a solid for which one of the side is in the region, and if you take cross sections, meaning if you slice perpendicular to the x-axis, what you find is a triangle whose height is half of its base. The base is in the region, the height is half of the base. I hope you can visualize what the volume looks like, what the solid looks like. I tried to sketch it here. This corresponds very much to the view we have here, but if you were looking from the opposite side, this is what the volume looks like. At any point, it's probably better to refer to this sketch. If you slice it, you would always see a triangle. So this triangle has a base B and a height that I called h. We don't need r anymore because we are not going to use the area of a circle. It's not pi r squared anymore, it's something else. For a triangle, in fact, we know very well that the area is base times height over 2. And in our example, we're going to have to figure out what the base is and what the height is. Once again, we are integrating in terms of x. How would I figure this out? Because if I look at a variety of these triangles, I notice that if I want to visit all of the triangles, travel through all the triangles, I'm going to start at x equals 0 and move along the x-axis until I reach the last triangle. It would make no sense to go upward along the y-axis. So, what is the base? Well, it's very similar to what we had in the beginning. The base is actually the value of the function, it's x squared. And in the question it is expressed that the height is half of the base, so the height would be x squared over 2. Once we put all this together, we get an integral from 0 to 3 of x power 4 over 4 dx. Finally, one more variation on this situation. We have a cross-section, again a solid defined by cross-section, but we are going to use volumes in terms of y. So how would that change? The region bounded by y equals x squared, the x-axis, and x equals 3 is the base of a solid, exactly like before. For the solid, each cross-section perpendicular to the y-axis is a semicircle with diameter on the xy plane. Here is our green region, and if we slice perpendicularly to the y-axis, what we would see from our solid would be a semicircle whose diameter is in the xy plane. The last part of the sentence means that the semicircles are sitting on the xy plane and they protrude out of the xy plane. It is said that it is a diameter, so from here to there we have the diameter of the semicircle. Let's think about what the area of a semicircle is. Firstly, let's have a look at what the volume looks like. It appears to be something like that. I hope you can imagine that from the graph there. Now, because it's a semicircle and we have the diameter lying in the xy plane, we will need to actually find the radius. That is going to be half of the diameter. So the diameter being 3 minus root y, like we've seen several times before, the radius is 3 minus root y over 2. Here there's something we need to be careful of. The area is a semicircle, so it's pi r squared over 2. But notice how the radius is also something over 2. So in the end, we will have two parts that are divided by 2. Sometimes it's a little confusing. We feel like, well, I've already divided by 2. You actually need to do it twice for two separate reasons. So we are integrating in terms of y here. Again, we can see I drew 4 semicircles, and you can see how you will visit these 4 semicircles by traveling along the y-axis from the first one all the way to the last one at y equals 9. When you substitute r equals 3 minus root y over 2, you get this expression, and you can extract all the constant in front of the integral. We have some pi again because it's a semicircle. Just don't put a pi systematically. It's only when we have circles or semicircles. Otherwise, if we have rectangles or triangles or squares, then there would be no pi. That completes our travel around all the volumes that are presented here, and I really think it covers pretty much every type of situation you might encounter in AP Calculus AB. Thank you.